Wait a minute. How did we end up with that? All right. Okay, so we are recording. All right, so now just to explain again what I'm doing. There is a traditional teaching session in the course called the Singularity Explained and Promoted. Most of that has never been tested on the exam, and the middle part is very depressing. So I've decided to leave that out this term and just present to you the few slides at the beginning that are actually on the midterm and sort of precede the depressing part. And after that, we will then go on to Simon Wu's quantum supremacy and to discussion about wait a second, let me read this here. Kind of want, oh, the whole Singularity musical now, yeah. Well, we haven't done that. That's something for the future. Yeah, but thanks for wanting that. I'm glad you want the whole musical. All right. So I'm going to give a short presentation, just the beginning part of my PowerPoint. I sent you the whole thing just so you would know what the rest of it is. And then we'll go on to Simon. So that's the plan. Okay, so. All right, the technological singularity explained and promoted. So this is the URL for the Singularity song you just witnessed. So the objectives: understand one should not fear complexity, do not seek the one great truth. There are many truths, they can be true concurrently. Understand the three main schools of belief about the singularity. Understand the four main paths to the singularity. Understand the history of the singularity, Marcus Hutter's main ideas about it. Understand the challenge of promoting the singularity, the idea behind Future Day and Longevity Day. Do not fear complexity. There's beauty in complexity. The real world is complex. Your significant other is complex. Perfect quadruple think with equipoise. What? Seemingly contradictory ideas can all be true, can find a balance between them. The future of transplantation is promotion of deceased donor donation until there are no more waiting lists, tolerance, tissue engineering, repair, and stem cell creation of new organs. In other words, a lot of different things at once. It's complicated. That's not bad. Peter Diamandis says, when faced with a choice between two desirable goals, choose both. Okay, so I'm trying to find an analogy that works sort of across cultures and with all students, and have chosen Lewis Carroll's Alice in Wonderland. In that story, a world is confronted that is much more organic than expected. You may recall that the segment which says the main difficulty Alice had was in managing her flamingo. So like the croquet mallet is a flamingo, the ball is alive, the mallet is alive, everything is alive. The world described as much more organic than expected. We face potentially exactly the opposite. In the technological singularity, we face a world that's much less organic than expected and could develop without us. So the three main schools of belief about the singularity: accelerating change, event horizon, and intelligence explosion. And there are four main paths to the singularity. First, you can create an artificial intelligence that exceeds human intelligence. Second, you can build human-computer interfaces that allow humans to go beyond their innate intelligence to a significant extent, cybernetic singularity. Third, you can find ways in biology to improve upon the natural human intellect, but you would expect that would be very slow. And fourth is where the internet wakes up, build large computer networks in which beyond human intelligence emerges. So one day you log on to the internet and it starts talking to you, and you realize it knows everything about you. All these different variations on the belief in the singularity are reflected in the courses at Singularity University. The experience of attending Singularity University, which led to the development of this course in 2010, 2011, is one that grows and grows upon completion of the course. Associated memories become more vivid rather than less vivid with time. They're on an exponential curve of their own. At least that's my experience. It's a picture of me in my Singularity University class. I always stick out like a sore thumb. You can see, I was the only person from like the academic world in that class. So Ray Kurzweil, who's the chancellor of Singularity University and the best known futurist in the singularity area, his views and intellectual exploration are as broad as that of the university he founded. So when you hear somebody criticizing him or arguing with him as if he held narrow, rigid views, that is a false straw man argument. He's accessible. You're able to write to him. If you write to him with some complaint about his writing, he will not only answer you very quickly and completely, but tell you something you had no idea existed. And it can be a very positive educational experience. Okay, what about the history of the singularity? Ancient history. In 1847, R. Thornton, the editor of the Expounder of Primitive Christianity, wrote about the recent invention of the four-function mechanical calculator, saying, "Such machines by which the scholar may, by turning a crank, grind out the solution of a problem without the fatigue of mental application, would, by its introduction into schools, do incalculable injury. But who knows that such machines, when brought to greater perfection, may not think of a plan to remedy all their own defects and then grind out ideas beyond the ken of mortal mind." So that's the first person who wrote about a singularity-like experience. In 1863, 4 years after Darwin published On the Origin of Species, Samuel Butler published a letter captioned "Darwin Among the Machines." It compares human evolution to machine evolution, prophesizing half in jest that machines would eventually replace man in the supremacy of the earth. "In the course of ages, we shall find ourselves the inferior race." The letter raises many of the themes now being debated by proponents of the technological singularity. In Erewhon, which you will all recognize as nowhere spelled backwards, Butler argued that there's no security against the ultimate development of mechanical consciousness in the fact of machines possessing little consciousness now. A mollusk has not much consciousness. Reflect upon the extraordinary advance which machines have made during the last few hundred years, and note how slowly the animal and vegetable kingdoms are advancing. The more highly organized machines are creatures not so much of yesterday as of the last 5 minutes, so to speak, in comparison with past time. That brings us to Marcus Hutter. The thing I want you to remember, Marcus Hutter, is that he has a more vivid idea of what the singularity will include, and that includes what it will sound like, which nobody else seems to know. And he believes that when viewed from the outside, the singularity will sound like white noise. And I can go ahead to the one slide that deals with that, which is here. Maybe a society of increasing intelligence will be increasingly indistinguishable from noise when viewed from the outside. So that's the part of this PowerPoint that you need to know. And so I will now stop sharing and let Simon take over. Okay.
Hi everyone. So today we're going to talk about quantum supremacy, which I hope will be less kind of in depth than my past few lectures, which were really into the quantum physics. This is more like the applications of it. So I'll share my screen for the presentation. Can you guys see my screen?
Yes.
All right. So quantum supremacy. So these are the objectives of what we're going to talk about today, which is what even is quantum supremacy. It might be a new term to some of you guys. We're going to brainstorm areas where we could apply quantum mechanics. And then 2 more topics. One is, how does it differ from the normal computers we have today? Like this, we're all on our computers right now. So how does quantum computers differ from the computers we use today? And the final is like ethical concerns regarding quantum mechanics. So let's talk about quantum mechanics. How is it defined? This is just like an Oxford Dictionary definition. But the key things here is it deals with very small things. And it's just a branch of physics. And how do we describe these small things? These small things that behave very illogically, very unintuitively, such as how they can be both a particle and a wave, how we can't ever be certain of where they are or what speed they're going at. So that's quantum mechanics. So how do these very small phenomena affect our big macroscopic life, right? Like before we even heard of quantum mechanics, Newton's laws really suited us really well, right? And even without quantum mechanics, I don't think our lives are, you might think our lives aren't really that affected, right? Because they're so small. So I think one way to think about this is, you know, in science, scientists come up with all these laws or rules and stuff like that, but there's really no unifying rule, right? It's like when we were a kid, you know, our parents are like, you can't do this, but the truth is it depends, right? And that's same with science. So a lot of these rules, it depends. So even though Newton's laws suit us really well microscopically, they don't work anymore because it depends. So we have to create these new laws. So how does quantum mechanics, what does it explain? So we're going to see that now. So let's talk about some applications of quantum mechanics. Now you see 4 here, like computers, smartphones, our telecommunication system, GPS and MRIs, but really it's quite endless. Like these days, financial modeling, or when pharmaceutical companies are testing their new drugs, or when it comes to cybersecurity, all of that is quantum mechanics. Or like these days, like predicting the weather, that's also quantum mechanics, quantum computing. So it's the applications are quite endless, and really quantum computing really comes into play when you're dealing with lots of data and trying to make predictions. So when you think of anything that involves predicting things, that's when quantum computers come in. We're going to go through all four of these applications in a bit more depth because they're just pretty good examples. I think all of these kind of apply to us on a day-to-day basis. So when we're talking about MRIs, like, although not everyone might know how exactly they work, we know, like, they're used in the healthcare setting. So before MRIs, we had like X-rays, and X-rays are great for detecting hard things, hard, dense things, like our bones, right? Like X-rays are mainly used to detect bone and sometimes a tumor, something very dense. And right on the X-ray, the bones are like white and everything else is like dark. The X-rays go right through. But the benefit of MRI is it allows us to look at soft tissue, right? Like muscles and stuff like that. So how does it do that? So MRI basically uses, some of you guys might be in chemistry, like organic chemistry. I think sometimes you have to measure like molecules, NMR. It uses the same concept. So it just measures specifically hydrogen, and it's spins and flips. But the way you can think of MRI is it just measures the amount of hydrogen anywhere. And the amount of hydrogen is like kind of your fingerprint for your body. So like your muscles might have more hydrogen compared to your fat, compared to your skin, right? All different levels of hydrogen, and MRI just detects different levels of hydrogen. So then you get to really a good comprehensive view of your body. And so that uses quantum mechanics, because when we talk about molecules and they're spinning and they're doing those quantum behaviors, that's why MRI actually uses quantum mechanics. So lasers, when we think of lasers, I guess we just think of like playing with our cats, but actually lasers are like, they're not just playing with cats, like whether it be like scanning our barcodes at the grocery store these days, all self-checkout, or telecommunication. And that's like our internet basically. So it's crazy. And what's funny is, like, even though Einstein's known for his like gravity and his his special relativity, general relativity, where he thought about how gravity might not just be a pulling force, but actually like there's a space time, and when objects have mass, they bend to space time. Even though he's most known for that, that's what he's most famous for. He actually only got his Nobel Prize on something completely different, and it was more related to like lasers and photons. So that's quite fun. I think he deserved more than one Nobel Prize. Who knows? But lasers, it's actually an acronym. It stands for light amplification of stimulated emission of radiation. But what makes lasers different from normal light, like we have light bulbs, is that when a light bulb emits light, all the wavelengths are garbled together, kind of like when you open the tap, you just see lots of bubbles garble up. I don't know if you've ever guys seen laminar flow. I know there's some YouTube channels that show that. Like there's a YouTube channel called Smarter Every Day, and that guy's like really into laminar flow. Right, that's just like his thing. But laminar flow is kind of what lasers are like, where all the light is kind of unified into one unified in sync wavelength. If you guys ever seen laminar flow, I think some hotels have it, where if they shoot a jet of water, it almost looks like a solid object that just flows in the air and comes down, right? You could never do that with a tap water or something, because the flow is turbulent. So you think of like our lights are like turbulent light, but then lasers are like laminar flow lights. They're just all in sync, right? And so that holds a lot of benefits, especially when it comes to information transfer, right? You're going to get more clear signals that way. Okay, now onto atomic clocks. Like atomic clocks probably doesn't affect our daily life, just atomic clocks alone, but every GPS satellite, orbiting our Earth has atomic clocks inside. What's the point of atomic clocks? Basically, like, we take it for granted that our phones just show the time. We just expect it to show the time every time. But how do we, like, what's calculating the time, right? It's like, how do we define time? So our time is defined by oscillations of atomic molecules, right? And those oscillations release microwave, just like when you turn on the microwave, you heat some food, the same wavelength, they release microwaves as they keep oscillating. And the frequency of those microwaves being released is how we define time. I think that's pretty crazy. Like, we also take one, like before the 1 kg, that weight, before it was defined, like we had like 12 kgs, 12 like samples of 1 kilogram, and they were like spread across the world. And so sometimes countries would check on each other's kilograms, but then they found out that each other's kilograms, the weights had diverged. So that's bad, when we define the kilogram based on these 12 weights, yet these 12 weights are changing their weights through time. That's not accurate. So now it's more defined by concept. I think it's defined by some isotope of silicon. So, even though we take these units of measurement for granted, we do need something to define it, right? How do we define it? So in this case, we just define it more as just the oscillations of an atomic molecule. I think it's cesium. And when it oscillates, it releases light in the form of microwaves. And that's how we define time, just based on the frequency. And I think you guys know, like, how GPS work is you need like 3 satellites and you need to triangulate your location. So 3 is usually the minimum you need to really know exactly where you are. And although, of course, we get like the lower level GPS satellites, I know, like, I've heard stories of like the US military, they can like shoot a missile right into our mailbox. That's how accurate their GPS satellites are. So, it's pretty crazy. And why is it important that these satellites have the same time? Like, what's the point of these clocks? Because, when the satellite receives signal from the ground up, it takes time, right? So if the time isn't synced, then you're not going to get the same measurement of distance, right? Distance is, I think it's velocity times, no, sorry, speed times time, right? So if your time isn't the same, then your distance measurement isn't the same, and they wouldn't be in sync. So that's the reason all GPS have atomic clocks. So let's talk about computers. And, when we talk about bits, that's like our computers, whether it be our cell phones or our normal computers. When we talk in English, we have that information system. I think it's 26 characters, right? Like A, B, C, D, E. But in computers, they only speak in zeros and ones, right? Which might be a bit more simple. When we start piecing words together, we have like a bit more possibilities, but for them, it's just 0 and 1. And so that's called a binary digit, and that's where the word bit comes from. It's kind of, again, a bit of an acronym. So there's kind of base systems. So for example, most computers read in like base 8. So 8 bits of information makes a byte. And so that's, when you have 8 bits, then you can form different words, different letters, right? But in some other computers, they might use like hexadecimals, which is like base 16. I think, we use base 10 when we're counting to each other, because I think some people say it's because we only have 10 digits on our hands, so that's why it made it more easy. But computers, they don't have fingers, so we just made it kind of base 8 for them. So groups of 8 kind of make a byte, and then that makes different letters and combinations. Just a quick thought. I realized, the world's universal language is kind of English. Everyone wants to learn English. But I think in the future, it's really important for us to learn coding or learn a bit of computer language, because in the future, how are we supposed to communicate with our phones and laptops? Software developers, they had to write code, like they had to talk to their computers and teach them how to speak English, or teach them how to display visuals. That's how at least we can communicate with our laptops or phones, because at least they show something that's understandable to us, which is like, the visual, how it visually looks and stuff. But in the future, I feel like most people learn how to talk to computers directly rather than have someone translate it to this visually appealing look. So I think in the future, it's really important if our future kids, or even us, take initiative to learn a little bit of coding and stuff like that, because I think it's very important. I mean, in the future, our fridges will be smart, our stoves will be smart, our microwaves will be smart, right? So the future is like, it's more computers and us. Hopefully we're allies, right, rather than enemies. So this was more classical computing, which it can only be 0 or 1. Now let's talk about quantum computing, which is the other side of things. So the main difference is they're not really limited to 2 states. It's not 0 or 1. They have quantum bits, which are called qubits. So these are just bits, and this is a qubit. Now, qubit sounds like 4 bits maybe, but it's actually not. So qubits just means that these bits can be 0 or 1 or anything in between, you know. So before these bits were just 0 or 1. Here they're defined by spin. So let's say it's spin up or spin down. So that's the two states a molecule could be. It's either up or down, or in between. It's like Schrodinger's cat, right? So the idea is here, you always know the computer is either doing a 1 or a 0, but here the computer, it's Schrodinger's cat. You don't see what it is. It could be up, could be down. The moment you need to use it, then you finally know. So the benefit here is you kind of get almost infinite states of in between 0 and 1, right? So you're spinning up or spinning down, and that's called a superposition. So when anything's in a superposition, when you're undecided of going where to eat, I guess you could call yourself you're in a superposition. You haven't made a decision yet. Same thing. So how, quantum computers aren't really going to replace our computers. That's like saying apples are going to replace oranges, right? That's how you can compare them. Like they're both computers, they're both fruits, but they're different kind of fruits, and they both have a different purpose. You're trying to make orange juice, you would use an orange, right? Not an apple. So what are the applications of quantum computers, right? Quantum computers, again, it's all about kind of predictive stuff and data stuff. So like when you're gaming, it's not like you're predicting, or when you're, using Zoom or, checking e-class, you're not predicting anything. You need the computer to do something for you very simply, following a simple algorithm. Press the button, show the picture. That's not predicting, right? That's something that's like just an equation. So that's not where quantum computers would help in any way. They're more helping with predicting stuff that requires, in some cases, they're actually 100 million times more efficient than a normal computer would be. 100 million. And they're actually like 1,000 times more efficient in terms of electricity use for certain applications. So, when you're trying to make apple juice using apple juice using an orange, that's not efficient, right? But if you have an apple, then you can make apple juice. Very bad analogy. But what's interesting is, we can fling our cell phones around or our laptops around, and they are not going to be damaged, right? But quantum computers are like extremely delicate. You have these molecules that are in a superposition, being up and down. They're so delicate. They're kept so cold. They're so isolated. They're on like they're almost like floating in place from all the suspensions, because they can't handle vibrations either. Super cold, super like isolated, almost like not affected by vibrations. So they're like a very delicate object, but if we can maintain that delicate state, then they can actually do really good help us solve really good computational problems for us. So this is just a quick summary of where the similarities and differences, right? So number one, normally computers use bits, but then quantum computers use qubits. That's just a word difference, right? But what does it mean? It just means that classical uses 0 or 1, but quantum can be 0 or 1 at the same time, superposition, Schrodinger's cat, right? Is the cat alive or dead, right? The quantum computer doesn't really, it's just floating that state until we need to use it, bam, then it slams into its state, right? So classical computers not as fast, not as efficient. Again, this is with the asterisk, depending on the application, right? Depending on the application. Whereas it's faster due to superposition, okay. Depending on the application. Yeah, so this is the key. Like classical computers for uses that don't need to predict things, right? You don't need to predict everything, right? And that's why classical computers will still be here for us, right? But when you need to do something that requires, you're really just trying to think in the future, basically. Like quantum computers, all about trying to predict something that you would have to calculate so many different variables, right? Like whether or not like someone's gonna be elected, it's not just the votes, right? A classical computer would never be able to figure that out, but a quantum computer would take in all the parameters, like how everyone's feeling that day, what's the weather, how does that affect that person, does that person have a job? All these things that require so much prediction on a large scale, that's where quantum computing comes in. So I guess we could watch a YouTube video that's really well animated, and maybe that could help us understand it a bit more. Wait, can you guys hear the audio first?
No, I think you have to.
Can't hear the audio.
Yeah, so just reshare the screen with the little like check mark thing at the bottom that
Right.
says share sound.
So
Okay.
unshare it and then turn on computer
Let me
audio.
drag this down. Okay. So unshare. Why do I feel like I'm super old? I can't even figure out Zoom. Where's the button?
So at the top, there should be a red
I
thing
see.
to unshare. Yeah,
Okay, so now I share with the check mark, right?
right, with the check mark for computer
I see. Share sound.
audio. Yeah.
I got it. Share sound. Oh, I need to enable sharing privilege or something. Or do I not have to? Well, why don't we see if we hear sound? If not, I'll disconnect and allow permissions or something. You hear it now?
Yes, we do.
Awesome.
Quantum physics, one of the most successful theories of modern science, describes the way our world works at the most fundamental level. Quantum computing has become one of the leading applications of quantum physics. Quantum computers have the potential to solve some of the world's most complex problems that are beyond the reach of even today's most powerful supercomputers. Quantum computers are not going to replace classical computers, but their radically different way of operating enables them to perform calculations that classical computing cannot. Let's see how they differ. Classical computers encode information in bits, and each bit can represent a 0 or a 1. These zeros and ones act as on-off switches that ultimately translate into compute functions. To perform a simple calculation, like solving a maze, a classical computer would test each possible route one at a time to find the correct one. Just as classical computers have bits, quantum computers have qubits. Qubits, however, make use of two key principles of quantum physics: superposition and entanglement. Superposition means that each qubit can represent a 0, a 1, or both at the same time. And entanglement happens when two qubits in a superposition are correlated with one another, meaning the state of one, whether it's a 0, a 1, or both, depends on the state of another. Using these two principles, qubits can act as a much more sophisticated version of switches, helping quantum computers solve difficult problems that are virtually impossible using classical computers. To illustrate how this makes quantum computers more powerful, let's look at some numbers. Take a classical n-bit computer, with n representing the number of bits. It can represent and examine only one system state at a time. An n-qubit computer, however, would have the power to represent 2 to the power of n system states and perform parallel operations on all those states at once. This means that every time you add just one more qubit to a quantum computer, the number of states it can represent and examine doubles. So a 50-qubit quantum machine could examine 2 to the power of 50 states at once. This exponential increase in power, together with the entanglement of qubits, is what allows quantum computers to solve certain problems so much more efficiently. While a classical computer solves a problem like the maze by testing each possible route one at a time, a quantum computer uses its entangled quantum states to find the correct route quicker, with far fewer calculations. Think of it this way. Technologies that currently run on classical computers can expertly find patterns and insights buried in vast amounts of existing data. But quantum computers will deliver solutions where patterns cannot be seen because sufficient data does not exist, or the possibilities for discovering an optimal answer are too enormous to ever be processed by a classical computer. Quantum computers could lead to the discovery of new medicines and materials by helping us untangle the complexities of molecular and chemical interactions. They could help the financial services industry make better investments by finding new ways to model financial data and isolate key global risk factors. They could even transform supply chain and logistics by finding the optimal routes across global systems, like optimizing fleet operations for deliveries during the holiday season. Quantum computing won't replace our everyday computers and smartphones, but its ability to solve complex problems will open up a new universe of information, transforming our view of the world and the way we navigate it.
All right. What a great video. Before we get to quantum supremacy, is this full screen? Sorry. Before we get to quantum supremacy, I want to. Do you guys know much about AI and stuff like that? Artificial intelligence. That's in computer science. There's like kind of, if you imagine a bubble, we have this one bubble, and that's in this bubble is all AI, right? Within AI, there's another bubble called machine learning. So it's a specific type of AI. Now we're in the machine learning bubble. And within machine learning, we have another bubble, and that's called deep learning. So there's kind of 3 layers of what's called AI. And what I found interesting about the deep learning one is, normally if we're saying, what makes this car good, right? Why would someone want to buy this car? It could be that this person once had a pet rat and they always like the shape of their pet rat. So now that influenced their decision to get this car that has that same shape, or because they're interested in speed, or because the hood has like vents on it, right? These are like visual cues or parameters that we can see or we can understand, right? But what's interesting about deep learning is that the computer, you basically build a neural network, right? So there's almost like a brain in the computer, and it has this network. But what's interesting is when this computer makes predictions, it's a black box. I think you might have already learned this one of the lectures in this course. It's a black box, so you can never know what the computer was even thinking. How did it even come to that decision, right? When the computer recommends a car, it could be looking at like the shape of the glass at that one point, and that's how it determined you like it. So I just thought like that's how quantum computers will really help with deep learning, in that because it can analyze all these states at once, it can really choose what makes something good or what makes something bad based on details that we would never be able to logically understand. So definitely really important for the advancement of humanity. So what's quantum supremacy? It's very simple. It's just basically when a quantum device, a quantum computer, does something better than a classical computer can. So even though this is all theoretical, in practice, the best quantum computer still can't beat the best classical computer, right? It all comes down to the number of qubits and the optimization, right? So I'm not sure what exact qubits we're up to right now, but quantum supremacy is whenever this moment in time that's irreversible, right? The moment in time when a quantum computer does something better than a classical computer. And at that moment, that's quantum supremacy, right? It's like the Industrial Revolution, right? It's irreversible. It's that moment in time when, a quantum computer that exists does something better than a classical computer can. And it's important when, this is just the amount of money in millions of euros. That's the unit. So Canada investing 100 million euros into quantum technology. And what's interesting, and this is non-classified technology, right? So just imagine, especially the US this is just the reported non-classified. Who knows how much money they're pouring into classified, quantum technology. But the point is, I guess the world realizes its importance, what it could do for us. So yeah, it just shows a really important thing. The whole world investing, what is that? I guess that'd be 1 billion, 1.5 billion euros. This is a unit of million. Yeah, I think, is that 1.5 billion? I think 1.5 billion. 1.5 billion euros every year on quantum computing and stuff like that. So, this isn't that recent, but Google often says they've achieved some sort of quantum supremacy. So why don't we watch their video talking about quantum supremacy? It's very educational.
The tantalizing promise of quantum computers is that they can do certain tasks exponentially faster than classical machines. And the quantum supremacy experiment is proof that this is indeed the case.
The word quantum computer is a little bit misleading because it sounds like a computer. And when people think of computer, they think of a phone or a laptop. The truth is the phone and the laptop and even a very powerful supercomputer all operate according to the same fundamental rules. And a quantum computer is fundamentally different.
classical bit stores information as a 0 or 1, and a quantum bit can be both 0 and 1 at the same time. If you have 2 quantum bits, then there are 4 possible states that you can put in superposition. With 3 qubits, it's 8, 4 qubits, it's 16. It grows exponentially.
The nice thing about quantum supremacy is that it is a very well-defined engineering milestone.
In a nutshell, what we're trying to do is we're trying to show that experimental quantum computers can surpass the best supercomputers in the world.
To actually demonstrate quantum supremacy, we have these 3 steps. First, pick a circuit. Second, run it on the quantum computer. Third, simulate what the quantum computer is doing on a classical computer. We gradually increase the complexity of that circuit. At some point, it becomes completely impossible for the classical computer to keep up. Then we say we've achieved quantum supremacy.
We started building together the quantum chips to do this experiment. And then the evolution of the devices were more and more qubits and more complexity. It's very much an iterative process.
A lot of the work that we put in was not just these chips, but is also the infrastructure that you need to drive those chips. The cryostats that we install them in, all of the control electronics, software, all of this stuff is needed, and it all has to be developed.
When the experiment started, we were getting data from the experimentalists. We saw initially a beautiful straight line corresponding to our predictions.
Then, right before we hit supremacy, it dropped much faster and it fell below the threshold where it needed to be.
And there's nothing we can do because we don't know how to analyze past that. So everyone's like, oh, we're screwed because it's getting really, really bad at large number of qubits.
It's like, well, maybe there's some really complex interaction between all the qubits.
It turned out that the reason was rather benign. We calibrated a little bit better and said that this problem disappeared.
So there wasn't like a, oh, we did it.
I think we crossed it, and then it wasn't clear that we crossed it, so we crossed it a little bit further.
It took me like a day to realize, like, hold on, this is actually experimental data. It's kind of amazing to see, how well the theory works.
The processor that achieved quantum supremacy is called the Sycamore processor.
And it's parallel processing 2 to the 53 states, which is 10 million billion. And thus that enormous amount of parallel processing is what gives it the power.
When we run small chunks of the computation in the largest supercomputer in the world, our estimate is that it will take thousands of years to complete the full computation.
Technologies are born this way. Let's say the space age started with a satellite orbiting Earth, and it was not doing much, it was just beeping.
The big technical achievement of quantum supremacy was really dependent on all this young talent who's kind of taken this and gotten it to work at a very technologically capable level.
We have reached a new computational capability. There are certain computations, the only place in the world where you can compute those things is here in our data center at Google Santa Barbara.
For the first time, we're showing that we can solve a problem that is just infeasible to do on the biggest computers ever made by civilization.
And what's exciting is now we're ready to turn this over to the world and say, let's figure out what we can do with this.
The thing that excites me most is building a useful quantum computer. When we can give a researcher a tool that is unlike any other and say, great, figure out something cool to do with it. Mankind is pretty good at that.
I think a really important concept they mentioned was like parallel processing. I think it must have been like 5 years ago, processor companies like Intel would brag about having like a quad core. That means they could do like kind of 4 things at the same time. And I think these days, the best processor on the market has like maybe 16 cores, 32 cores. I think some servers have like 64 core processors. That's only 64 simultaneous events they can calculate at the same time. Whereas, this Google quantum computer has 2 to the 53, has 53 qubits, which means they can, like I said, they can calculate 10 million billion simultaneous things at once. That's just phenomenal. So this is where we all get to talk about the ethics of quantum computing. So I want to hear what you guys have to think about what you think it means for and I'll get it started. You know, we all have passwords. I mean, that's all gone once quantum computers become mainstream. Because while a classical computer has to brute force and try every single password at once, or you know, the reason why like sometimes our passwords get cracked is because some hackers break into some server and they get a library of passwords, and that's the only way you can crack passwords faster is if you have a library in the first place, and you can like kind of know what passwords are generally like, but still it's kind of brute force. You still have to like try every combination, whereas a quantum computer would just try every combination kind of at once, and that'd be not great. So that's one application. All our banking security, that's all gone as well. So, you know, what do we see the future of quantum, how quantum computers will affect us? At the same time, there's a theory that says like the forces of quote unquote good and bad are always long term, they're balanced. So just as quantum computers can be used for bad things, they'll just as well be used for good things. So maybe our security systems will also be powered by quantum computing. So it doesn't matter if a bad person has a quantum computer that can break the passwords will now be protected via quantum computers. So maybe that's not a worry. But what do you guys think about this? That perhaps a pregnant woman, a doctor could use a quantum computer and predict everything that that child or person might end up having in the future. You know, just in terms of predictions, like being able to predict so far ahead, what do you think that might mean for us?
You know, I've never understood the concern about passwords because, you know, at least for me, like my, you know, my phone, my computer, my accounts, you try it 10 times, and if you have the wrong, you know, input, it will lock you out or it will erase the device. So, you know, like, wouldn't that be an effective safeguard against, you know, like, sure, this quantum computer can try like all the passwords you could possibly imagine coming up with, but it only has 10 tries to get, you know, the right result. So is that a potential safeguard against quantum computers?
That's a great point. So I know Apple is a really big advocate of hardware security, and hardware means that it's just built right into the chip. Like you said, 10 times doesn't work anymore. But I think where quantum computers will kind of break that is not on the hardware side, but more on the software side. We all have Google accounts, Facebook. On the interface to us, the front end interface, it says 10 tries, but I mean, hackers aren't going to go on the website. I think they go straight to the back end, straight to the server side. And the server is not going to tell them, oh, you only have 10 tries, right? And that's where the quantum computer can break it. Like these big companies like Google and Facebook, they literally hire hackers to try to hack them every single day so that they can build better security. So in the future but you're right, like in terms of hardware and coding, that's like, you can't really break that, like you said. So that's a really good point. I have never thought about that, but I think that is one way we could prevent it. Having something hard, a hardware, right? Like a quantum computer is never going to break a physical lock. So that's a really good point.
I have two comments. Firstly, to sort of answer your question, Thomas, it's interesting because AI is already being used by like Google and other bank services because they look at your activity, and if that activity is irregular, you know, then you get a notification for it that something's up, check on your account, maybe cancel it, you know. So AI is already being employed, so I can certainly see quantum computing being employed in a similar way. Sort of a more specific question next is, how will viruses look like for quantum computing?
I mean, yeah, at the end, like a virus at the end of the day is kind of like a human virus in that it's just a piece of code. And you know, a real virus like COVID, basically it takes over our cells, it makes our cells make more virus. Like every virus is kind of like that, right? Hijack some cell and make that cell a virus producing factory. And that's how like computer viruses are kind of similar, right? It's some piece of code that makes a computer make more of that code, and that's a virus. So I have no idea like how you code a virus in the first place, but to make a quantum virus, you know, that would be devastating. But that's where that some people talk about this philosophy of good and bad. Like some people say like it's always balanced long term because there's always going to be good quantum things and bad quantum things, and it's a race. Like bad quantum things will always try to take over and good quantum things will always try to take over. So it's a really good point. Have you guys heard of Bitcoin? You know, like the way that's kind of blockchain technology, and the way that works is if the majority is good, then no hacker can ever take over Bitcoin. Like Bitcoin works because the majority of computing power is supporting it. And if there's ever a case where the majority is on the opposite end, then Bitcoin will fall apart. So I don't know how quantum computing might affect like those cryptocurrencies and stuff like that. Because how they work is people just run their computers and try to solve these hard problems. But if a quantum computer can solve it just like that, I don't know what that might mean. But ethically, oh yeah, go for it.
Another question from me is, as we've seen from the two videos, like there's two main players so far, mainly Google and IBM. So depending on, I'm like thinking of this in a sort of space race way, depending on who reaches this quantum supremacy, supposedly Google has already reached it first, and the company that figures out, you know, how to like apply it and make it available to more people. What do you think the implications will be for the future? You know, having an almost monopoly of one big tech company sort of controlling most, if not all, quantum computing.
Yeah, that's a question right there. Holy moly. Yeah, I mean, all these companies, especially in the US, they're always facing like antitrust laws, which is like basically saying they don't have competition. And every time some small company does something a bit valuable, they always get bought out, right? Like Facebook's bought so many companies, whether it be WhatsApp or Instagram. So whenever they feel threatened, I guess they just buy those companies out, which isn't great. Another advantage these big companies have, they have data, right? Like that's something you can't just have because they have so many users. They just get that data. And I think data is the most valuable because all these computers really work off of having lots of data. Like if you're trying to start a company, you can't just have that data right off the bat, right? So that's one advantage they have. And you're really good in pointing out that like all these transactions are run through a bunch of algorithms. Like every time you tap your credit card, that transaction runs through like thousands of algorithms from the bank to check if it's fraud or something like that. And after that clears, then the transaction goes through. So yeah, what might it mean? I guess it makes us feel powerless, kind of like we're not in control, I guess. What do you think, Dr. Solez?
Yeah, I think there will be a great advantage if the company that achieves quantum supremacy first handles it in a model way that you know, other companies can replicate in the future, where when you have something that the whole human race can benefit from, it doesn't make too much sense to irritate everybody by just setting it up so you increase, you know, racial and ethnic disparity and make all the problems of the world greater. If you can set it up in a way that brings people together and makes people more equal and improves quality of life for the maximum number of people. So, I mean, it seems to me that's the logical way that they would handle it. And they'd get a huge PR benefit, right, from doing that. It would be regarded as a very beneficial thing in, you know, the history of the world that this was handled in such an equitable and broadly, you know, humanity enhancing way. So I could be wrong. I mean, their motto is "Don't be evil," right? But anyway, who knows what will actually happen?
Yeah.
For me, I'm most interested in the application of quantum computing to be able to like simulate real world stuff. Because if you look at like a chemical reaction, an animal, a human, there's lots of molecules and whatever else that compose that physical object, and it's very difficult to model those in computers. I understand that it takes extraordinary resources even to do very small models. But with, I guess, quantum computing, you can do that on a much larger scale, and you can invent all sorts of drugs and maybe model animals and animal interactions and model humans and maybe human consciousness, and I think that'll produce a great value for people everywhere.
That's such a great point. Like imagine like every time you see an animation of like protein folding or something, that's done like after days of rendering it out. But imagine being able to see it live, right? Like every single hydrogen molecule, you coded in all its van der Waals forces, its hydrogen bonding, all of that London dispersion, and you have millions of hydrogen molecules around. Imagine this computer being able to simulate all of that live in real time. And same with Pixar. Like every time an animator is animating, it's not even live. Like they have to like code it in and then send it to a render farm, and the render farm takes days to finally show you what the image looks like. But maybe quantum computers will allow animators and stuff like that to see things live, or a scientist to see a reaction live as it happens. That's such a great point.
So I wanted to make sure that we spend some time talking about the midterm. Why don't we do that for a little bit, and then we can come back to other things afterwards. So this midterm is sort of misnamed, right? It's after all the lectures in the course, so it's a bit like a final exam, but it's not a final exam. It only counts 20% of your grade, and it's a take-home midterm. And the other thing you have to do during that same period of time of April 1st to the 6th is to complete the course evaluation. And of course, on the 6th, that's when your paper is due for the course. So anyway, it's sort of interesting thinking about that. I don't think that you want to devote all those 6 days to this course. It doesn't make sense. The midterm probably takes 2 hours to complete. Let's say that, originally the idea was that it takes 80 minutes, an 80-minute class period. So although you have from April 1st to April 6th to do it, you obviously shouldn't, devote a huge amount of time, more than, say, the 2 hours to it. Okay, so there are 4 components. There's the regular midterm for the rest of the things in the course, which I am grading. There's the space and future prediction part, which Shauna Pandya is grading, the quantum biology part, which Jack Tuszynski is grading, and then the ethics part, which Michael Van Manen is grading. One important thing, I think, is you have choices of which questions to answer. So in the ethics part, it's 4 out of 6, and in the quantum biology, it is 4 out of 7. So if you answer all 7 or all 6, you'll probably only count like the first 4. So just remember that there are choices. You don't answer every question in those sections of the exam. Nothing terribly bad would happen, but it's just sort of a waste of your time if you actually answer every question when you're only required to answer 4. Okay, and then in the quantum biology portion of the midterm, remember the broad background of the students taking this course. There's students from, the arts and all sorts of different disciplines, and students from nursing and so on. So we cannot require you to do formulas and calculations. So you're not required to know formulas or to use them to get the answer. Describe the answer to the quantum biology questions in words, right? And sort of big concepts, like just exactly what Simon's been talking about. What are the key differences between classical physics and quantum physics? What point in history are we at? What is similar between physics at the turn of the 19th and 20th century and biology today? Are we going through a similar revolution in physics within biology today, similar to what occurred in classical physics in the 19th, at the turn of the 19th and 20th century? What are a few examples of quantum effects in biology? Be specific. What are the main objections to using quantum physics in the context of biological systems? It is obvious that many things cannot be explained without quantum, like the sense of sight and smell really are impossible to explain without quantum. But what are the objections to using quantum physics in the context of biological systems? What are some features of quantum mechanics that would be very useful in biology? What are the allometric scaling laws in physiology? What is their connection to quantum biology? And what is the amount of power consumed by the human body on average and the human brain? And what can it say about our efficiency as a biological engine? So those are the kinds of questions. None of them require you to calculate anything. And they give you an armamentarium of very interesting knowledge that, like at parties, you become the most interesting person to talk to. If you study for quantum biology part of the midterm, yeah, your social life is guaranteed. I'm just kidding, but anyway, there is some truth to that. So any questions about what I've just said about the midterm in general or the quantum biology part of it? To some extent, you can think about an open book exam where you maybe know beforehand what you have to describe. It still is hard to describe it if you don't understand it, right? So you have to do enough studying to kind of understand the basic concepts in quantum. And yet you would realize that all those slides with like formulas and stuff, you don't have to know the formula, you don't have to know what the formula means, and so on. So this is not an exam where we're asking you all sorts of obscure minutia that's buried in the PowerPoints, right? If you imagine, Jack, I forget how many slides there are in Jack's slide set, but there's like 120 or something. So it's a lot of material. We're not going to drill down into the most obscure slide there and ask you a lot of detailed stuff about it. So is that clear? Does that make sense? Any questions about that? Wow. So is that a good silence or like a stunned silence? So, yeah. Okay, good silence. Okay, well, that's good. Okay, so let's go back to Simon now. Wow, it's even a heart. Yeah, good. Okay. All right, Simon, back to you.
I just had one thought. I learned, I think yesterday I learned this, which was like, why do humans have war? Like in the past, it might have been like, you know, for territory and stuff like that. But these days, people have war, especially the most recent ones, are because of energy. It's all because of energy. And there's a trend where whenever we solve major energy advancements, everyone's standard of living increases and we have less wars. So one application of quantum computing could be towards solving energy. You know, right now on as amazing as Tesla is, the truth is their batteries are really similar to the one that was invented in 1960. It's the same concept of battery. So they're really limited battery wise. They make a lot of optimizations to the battery, but it's still the same idea of what a battery is. And so quantum computing can make a big impact in terms of energy. I always wonder, like, is wealth a zero-sum game? And by zero-sum game, I mean, will there always be people that are poor and always be people that are rich? As a zero-sum game, it means it all adds up to zero. So some are plus, some are minus. But I don't think it is, because although wealth might be, I'm not sure about wealth, but in terms of well-being, I don't think that is. I think human well-being can always be increased. I think right now we're living better than ever than we used to be. So at least human well-being is not a zero-sum game. And that's my opinion. So in that sense, like I think quantum computing, when it can help solve our energy crisis, then it'll be really beneficial to us. I really like how Elon Musk, you know, he mentioned this, which is that sustainable energy is inevitable. And by that, I don't think he means that like if we sit around, we're gonna reach sustainable energy. What he means is if we don't solve a sustainable energy, then all of human race will die, right? So if we're still alive in the future, it means it's inevitable. So obviously, like sustainable energy is really important. And by sustainable energy, it means that we take just as much as we give back to the earth, right? Right now it's not sustainable, we're taking too much. But you know, if quantum computing can help solve these big problems, then it'll be great for us. So that was just my thinking about, you know, the well-being of humans. It's not a zero-sum game, I think, so it'll be good.
At the same time, I do think there's something to be said that we can't put all of our hopes in technology necessarily, like even with electric cars. If we were to replace all of our current gasoline burning cars with electric cars by 2050, as many automobile companies have said they would, it doesn't really solve the problem because we're still mining like lithium and other heavy metals like unsustainably to make sure that everybody has an electric car. I think there's definitely a place for that, but also we need to focus on sort of investing into technology that can be used by everyone. So better LRT and like train systems that are used by everyone and that are sort of more equal in a way, because I mean, not so much when it's not free like in Edmonton, but anyone can use LRT for $3.50. Not everyone can afford a gasoline burning car. Not everyone will be able to afford an electric car. So I definitely think there's a balance between, you know, putting our hope in technology, but also working towards improving our current patterns of consumption and like interaction with the city and like structures of how we like structure housing and transport and things like that.
That's
a
that's
great
true,
point.
but it's also important not to fall in the trap of thinking some components of life won't change at all. Like, let's say the rarity of lithium. You know, asteroid mining, which is very likely to come on stream at some point, is really going to change resources, because a lot of rare elements now are present in large quantities in asteroids, and so when we're able to mine them, it will make a lot of things much easier and more widely distributed than they are now. And there are many other things like that. So it's not like you can take like your whole life and say, well, 50% of it won't change at all, and the other 50% is going to have this exponential change. That's probably not true. Everything is going to change. There'll be more options for how to do everything, how to get everything, how to be what you want to be, how to do what you want to do. All those things will change.
Here's a question from me. Is it ethical to mine minerals from asteroids? Isn't that just enabling our current exponential patterns of consumption that are currently limited by what the Earth has? We're just sort of continuing that into the future, in my opinion. Like, it's just prolonging the inevitable. Like, I don't know. I think we have a limit, and we're gonna reach it at one point. We might try to stretch it as much as we can.
Remember that I told you the one wrong answer in this course is peak oil. You're getting close to describing peak oil. That really what life is about is oil. We all need oil for everything. And at some point we're going to run out of oil and start fighting each other and kill each other off. That's a theory of peak oil. And that is so wrong. I just want any of you who kind of have this in the back of your mind, if that's what's really going to happen, that is so incorrect on 1,000 different reasons. You know, that every day the Earth receives enough radiant energy from the sun, you know, to more than take care of all of our energy needs, if we could just capture it all, and so on. So, and what's right and wrong changes. Think about the first test tube baby, how controversial, and people were tisking and, oh, this is awful that this is happening. But really a lot of good things came from that, and virtually nothing bad. So many advances are going to be like that. It's a big change. It makes things easier, but there are not huge adverse consequences. Whatever it was, why 10K? So the huge problems that were supposed to be brought about by ending the 1900s and starting the 2000s, why that just didn't happen. We all prepared for something awful to happen. And the moment we went from the 1900s to the 2000s, and it just didn't happen.
You know, I think Kim is definitely spot on. You know, the history of humanity is the history of the triumph of innovation. You know, the pie gets larger. Everyone, you know, on aggregate is better off materially. So it's certainly not a zero-sum game. I agree with you, Simon. And you know, markets respond. Incentives will change, and markets respond. People respond to the conditions on the ground. So it might not mean mining asteroids. Maybe there are more economically efficient ways to produce the resources we want. But the result will be found. And you know, I think space is our playground. You know, we heard lots about lots of stuff about space. I think it's excellent if we want to go and find different elements and use different resources in space. And you know, I'm seeing in the chat now, you know, that we overconsumption, overpopulation are not problems. I think, you know, we misuse some of our resources now because the incentives don't exist to use them properly. But you know, sometimes you have to reach a point where there's a real problem before people change how they behave. But I agree with the point about peak oil. You know, people always point to these issues and say there's peak blank, you know, peak food shortage or peak mineral shortage, or you know, there's always some resource you can point to and say that, oh, when that runs out, there's going to be a big problem. But that's never been the case, as markets and free enterprise and individual innovation has always enabled people to find creative solutions to any deficiency that we have of any resource.
Yeah, and you see, AI can help us figure this out. Like, remember my graphic of you know, the world in 2050, you know, with just deserts in the continents and oceans filled with plastic. Well, that's what happens if we don't have AI help us. But if we do, there's no way that will be the outcome. They can help us figure out many things that we cannot intrinsically solve ourselves. It'll be good.
But at the same time, isn't that almost a cop-out for us? You know, we'll just wait around for AI to solve it.
No, it isn't, because AI is not going to do it independent. That you know, all the strong efforts to, you know, address climate change now, AI will build on that. It's not they're going to start over or not pay attention. No, everything that has been suggested to solve nuclear war, you know, and climate change and the other big problems that we have. I talk about male against male aggression, but male against female is also important. Yeah, those are all very complicated problems, but they're not more complicated than protein folding. So if narrow AI can solve that, it can solve the other things. Yeah.
I have a question.
Yeah.
So until those technologies are developed, where we see the exploitation of Earth and peoples around the globe or around, on Earth, and like all these like different ethical issues rising and so on, what do we do in the meantime?
Well, transitions are not impossible to figure out. I mean, humans are adaptable. We've been figuring out transitions the whole history of humankind, right? So you're simply describing how do we solve those things based on the situation right now. And we have some ideas of what are approaches that work right now. And then how will we solve them when we have other things to help us that we don't have right now? And what should the transition between the two, how can we make positive change as rapidly as possible? You know, I don't know, what is the best way to think about this? You know, gentlemanly behavior, whatever. But there are a lot of things that we assume will be problems forever that are partially solved in sectors of our society. There really are ethically diverse groups working in great harmony and that sort of thing. There are men and women working together in very equal ways. And so you can take the fact that there are areas that have already solved these things. We just need to expand it to the rest of the human race and say, well, okay, how can we do that? So I think that the fact that many of these things have partial solutions already is quite, encouraging. Yeah.
I have a question for Nadia. Like, how do you imagine the future of humanity? It's true, like, I guess Earth is kind of a closed system, but sometimes we get asteroids coming in, so we get more net volume of Earth. But overall, it's a pretty closed system. So as we keep mining asteroids, bringing them in, then it's not a closed system where we're taking, right? And like you said, maybe our mentality or attitudes in North America aren't great for overconsumption and stuff like that. But would you imagine a future of humanity where we kind of populate some of the planets in the solar system, maybe Mars, maybe more habitable places like that? And so although Earth is our home, now in the future, maybe our civilization is more interplanetary. Do you see that in the future, or you don't think that's a future for us? Because then mining asteroids is kind of part of it, I guess,
Like, I'm not completely against it. I just do think there's something to be said that we should think these things through. Like, especially, I was just thinking about like the context of settler colonialism. Could that be applied to making colonies on the moon and Mars, even if there's nobody living there? We got to think about these things. Like, we're already destroying one planet, so are we going to go destroy some other planets? Like, it's a very pessimistic view, and obviously I think humans have so much potential, and that we're gonna need to explore space and develop these innovative solutions. My one qualm is that, like, within the current structure of economic and political systems, I don't see the possibility of human-driven change that works within those systems. I think we need to start rethinking about how we can restructure those systems and how we think. For example, overconsumption. In North America, there's the huge sustainability movement and zero waste movement of people rethinking, how much they're consuming, how much they're buying, where they're buying from. And I think those sorts of things are really important because they sort of take a step back, pause, and question, why do I need to buy this thing? Why is this ad telling me I need to buy this thing? Like, I don't know how to explain it any better than that, but that's sort of where I'm coming from. And I do tend toward pessimism at first, but I do think that as has been shown by humans multiple times in history, we have infinite possibility and infinite innovation and hope.
That's a really good point. Like, in the kind of quote unquote rules of the earth, overconsumption will lead to all of us dying, right? Because we use more than we give. I guess evolutionary, has overconsumption, wanting more, helped us survive? Is that a good trait to have, I guess, for humans evolution? Maybe it's helped us survive, just being so into getting more, discovering more, but maybe it's reached the limit. But if we're able to, one thing I worry about is, if you go to a new planet like Mars, how will that government be, right? They're the first ones there, how that government be? One good thing is, like, if aliens do exist out there, I think it would really unify Earth, because right now, we're separated between countries, but if there is one common entity that's not us, I think that would really unify us and be more cooperative, because I think that's why I sometimes wish there is an alien out there, because then it feels more like us. It's like us and we're exploring space together rather than like between countries.
Point out to each of you who maybe hold contrary opinions is that the plan we think is that, like, the colonies on Mars and so on will make their own rules. They can start with whatever laws from Earth they wish to, but will make their own legal system and system of morality that works for there. And I mean, life will be different if it's true that the radiation means that most of the regular humans like us have to live underground because there's too much radiation on the surface. So that would make for a different life, obviously, and maybe should have different rules. But yeah, so I think it doesn't mean that these are insoluble problems.
Yeah, I think that's a really good point. And it'd be interesting if, one country sort of sets their flag down on Mars, whether they're going to implement their status quo or if it's going to be a collective international thing in between the countries. We'll have to decide on the best sort of way of living on Mars, or if Mars is just going to become its own separate entity and we might have wars with Mars from Earth.
Well, but there'll be many fewer people living there, so, and it takes a long time to get there. So on, so it's sort of hard to have a very, 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 very long distance war, right? So, yeah.
Mars and Earth will just angrily tweet.
Yeah. Yeah.
I wonder if there could be some sort of collaboration that can be extended past what we now consider beings. Like, I'm stemming from indigenous, like, Cree worldviews, where we see that we're in relations with, like, the earth, with the iron and the soil, with, like, the air and the water and the skyways and everything like that. So I wonder if there will be an invitation where it's not really an invitation. We're just like starting to recognize that, like, we coexist, and maybe that will help with like expanding how we see and how we develop and plan, and also like make policies when we include, like, let's say, like, livestock, not as just like property, but as like beings that we like have relationships with, that doesn't only define in like a hierarchical way or like rely on power relations or power assumptions of like abilities and stuff like that. I wonder if that's gonna be really like what we need to do in order to make a progress that's gonna be the most sustainable, but also ethical, because we're kind of collaborating and including people in, not just people, but like other existences in the universe that we are able to like interact with. Like, I wonder if that's gonna really push us over to making those breakthroughs that might address a lot of the concerns that I have personally, but I think, Nadia, you also have. And it will probably, I think, will address a lot of what Taryn discussed when we were talking about ways that like transhumanity or yeah, like this could possibly become a new force of neocolonialism. I think like collaboration is gonna really help with that. But I think that's gonna take a lot of unlearning of what we think is good and what we think is bad, and like breaking out of those binaries, and moreover, who we think can be contributors to what we're talking about when it comes to technology and building policies and stuff like that. I think that's like still very much of a thing that doesn't get considered in. Like, are we gonna be able to build in what we think are like tribal technologies, where like making houses out of certain material that was historical, like maybe that's not sustainable anymore because like we just assume that that's not the best material. But then when we actually try different models of like building houses that are sustainable, it turns out that like the materials that were traditionally used by different tribal people are the best for the local like land and climate and stuff. So I wonder if like that's something that we can start considering. And like if we are, then like maybe we need to do more. It just seems like we can't just like assume and agree that, one, that we all want this to happen, and two, that like there's things that we want and things that we need to overcome, but different people in different positions of places are going to have different priorities. So then, like, are we really having those conversations that's connected? And at the same time, it's like, how do we know that this is what we actually need and what we actually want when the people that are marginalized often don't have these ways of like vocalizing these? Like, do these trees want us to have this technological development? Like, are they gonna be beneficial or benefited by this? And like, am I gonna be benefited by these trees wanting to have these things? You know, like there's just like so much that we need to talk about and like realize there's relations that I think are often getting overlooked.
So I think one way to look at it is for almost everything that we want to solve, having multiple very different vantage points will help us get the answers that we need quicker. So by shutting out voices, by not listening to people, it actually slows us down. And if we really have an open system of, you know, considering everybody's point of view, we'll make the most rapid progress. So I think it would also be nice when we finally encounter aliens if our culture seems superior to theirs, right? We have lots to teach them, you know, and they're saying, wow, we had no idea, you know, rather than the other way around where it turns out they have all the great ideas and we look like idiots, right? So that's the other way to think about it. Think of that first encounter and how embarrassing it's going to be human, you know? Let's make it so it's not embarrassing at all. So we're proud to be human and we're proud to be diverse and, you know, having all these varying points of view. And when we reach a point of needing to solve a problem, we're able to solve it because we're accepting all these varied vantage points. So
I have a question. Do you think that it's going to be technology that makes the first contact with aliens or humans? Like, is it going to be, sorry, I have cat hair everywhere. Is it going to be like people? Because like what this is reminding me of is when the Europeans made the first contact in the first cusp of contact with indigenous peoples, at least in the context of Canada. Like, I don't really know much about the indigenous histories of US and the scholars, what they have to say, but because they just like assumed that like European way was better, right? Like that it was superior. So I'm just wondering how like that bias would be eliminated. So I feel like maybe technology would be much better in terms of like preventing neocolonialism happening external to Earth. Maybe, I don't know.
Yeah, but think about, suppose that we don't make first contact until after machines are smarter than we are and everybody who makes their own decision fails, right? If you decide on your own who to marry, what to do with your life, where to go, where to live, so on, you end up with a very chaotic and unsatisfying life. If you ask the sentient machine, your life turns out great, right? So if we go from that point then, and we still haven't met aliens, when we meet aliens, that's going to be a really important question, right? So we're not going to try to solve it ourselves. We're going to go to the same sentient machines that help us solve who to marry and what to do with our lives and so on. So what should we do about these aliens, right? And that's likely to be much better because the machine will say, let's start with the assumption that they might be way better than we are. Lots of things we can learn from them. You know, there's no reason to impose our society values on them. Let's see what they've got. It might be a lot better than what we have, right? So, yeah. So I think that it is likely, I don't know for sure, that will be the sequence. That already every human on the planet knows in the sense that we are second-class citizens, but very happy second-class citizens, because all these big problems have been solved by this smarter entity represented by AI, you know, that like our trashing the earth stopped when AI took over and figured out how we could stop trashing the earth, right?
Dr. Solez, I have one question that I've been thinking about. Do you think AI would ever get tired of us and be like, look at these dumbass humans, let's get rid of them, and then like get rid of us? Like, I've been thinking about this. Like, will they want to engage with us and like entertain us? And like, will we, yeah, like, I don't know
think
if
they are our children, right? Think of it that way. And isn't it nice to have really smart children and children that can do more than the parents? So that's what AI is. It's like we're giving birth to them. That's kind of cool because both men and women can give birth to AI. It's absolutely equal between the sexes, right? And so thought about that way, we're proud of them. They are our progeny. They're proud of us. We're their parents, and they're trying to sort of help us and be nice to us and find us good places to live and keep us happy, right? So, and whose ideas are those? Are those my ideas? Those are Rich Sutton's ideas. So remember, when it comes to the midterm, you're required to know what his ideas are, right? They're on that one slide. Yeah. So, yeah. That's what he thinks. And he may be right. Probably is right. So there. Okay, we're getting down to rarefied. There are only 4 of us now. So anyway, we probably can't keep this video going forever because then nobody will watch the end of the video. You know, it got down to only 5 people and they kept going and going. And they thought somebody was gonna watch them, but there's no way I'm gonna watch the rarefied end of the video that only has 5 people in it. Yeah. So anyway, thank you. It's been a great session. So next time we're going to talk about COVID-19. There's no way that you're not interested in that because it's impacting us all very heavily. And then after that, on the 1st, there's no class basically, unless there's some huge problem with, you know, the midterm or something and you want to, you know, interrogate me about. But otherwise, there won't be any class on the 1st, but the 1st is when you start the midterm. And then the 6th at noon is when you send me the filled in midterm and the course evaluation. And then the 6th at 2 p.m. is when the first student presentations are. We have 3 per day over those 4 days. And I expect them to be really interesting and really good.
Oh no.
Yeah, that's my prediction. Okay, all, thank you very much. Thank you, Simon. Great session. So, okay.
Bye.
Bye-bye.